Hello dear students, welcome back to the series of lectures on theory of semigroups with course code MMTE 405. Today in this lecture we are going to discuss simple and zero simple semigroups. So let's first define a simple semigroup. Then we discuss some results on that class of semigroups, simple and zero simple semigroups. So first we define simple semigroup. Simple semigroup. Simple semigroup. A semigroup without zero. So that's the first condition, it should be without zero. A semigroup S without zero is called simple. Is called simple if it has no proper ideals. If it has no proper ideals, it's the definition of simple group, which has no proper normal subgroups. If it has no proper ideals, that is if I is an ideal of S, then this I should be equal to S. It has only one ideal, that's S itself. Now next we define a zero simple semigroup. A semigroup S with zero. So it's a semigroup with zero. A semigroup S with zero is said to be or is called a zero simple semigroup. To be zero simple semigroup if first property zero, because zero is an ideal of S, zero and S or the only ideals of S, only ideals of S, and second property S square not equal to zero. S square not equal to zero. Okay. So this second condition, it will exclude the case that that S is not actually the two-element null semigroup, because for if S is a two-element null semigroup, this excludes the case that S is not two-element null. Suppose S is a two-element null semigroup. Suppose S is equal to say 0 and A. So null semigroup means product of any two elements is 0. So then in that case this I equal to in that case this is trivially it's an ideal. You can see it's a zero simple semigroup because this zero is not the not the ideal of S, as if I take say A equal to 0, A equal to A, this one is not an ideal of S, because if I take the product of any element of A with any element of S, it's always equal to 0, and that does not lie in A. Okay, so it's not an ideal, because here A into A it's equal to 0, so it's not in A. So this two-element null semigroup. It's called two-element null semigroup. Two-element null means that the product of it's a semigroup with having two elements, and the product of any two elements is equal to 0. So this S square should not be equal to 0. That's the second condition for the semigroup S to be a zero simple semigroup. So first condition, 0 and S are the only ideals of S, and second condition, S square is not equal to 0. Okay. Now we are following a remark here that we are going to prove. Let's So let's say this, write this as an exercise. Show that S is simple. Show that S is simple. Show that S is simple. If and only if the relation J relation is equal to S cross S. Okay? The G relation is equal to S cross S. So you know the J relation. A and B are J related if and only if the two-sided ideal S1A S1 are is equal to the two-sided ideal S1B S1. So then those two elements are said to be J related. So that J relation should be equal to S cross S. In other words, any two elements of S are J related. That S is simple if and only if any two elements of S are J related. Let's solve this exercise. Suppose S is simple. Suppose S is simple. As we show that any two elements of S are J related. Now let A, B are any two elements of S. And then S1A, S1, it's a two-sided ideal. It's equal to S. Because it's a simple semigroup, S is the only ideal of S, but S1A, S1 is an ideal of S. And S1B, S1 is also an ideal of S, it's two-sided ideal, it's equal to S. So therefore, S1A, S1 is equal to S1B, S1, which implies A is J related to B. So that means any two elements are J related, which implies the J relation is equal to S cross S. It is the universal relation actually. In that case, if S is simple. Next, we assume that suppose any two elements are J related, or we can say that the S is the only J class, because it's any two elements are J related. That means it has only one J class, that's S itself. So conversely, assume that J is equal to S cross S, then S is the only J class. S is the only J class. Okay? It is only one J class, that's S itself, because any two elements are J related. Now, actually, we need to show that this S is simple. So for this, we show that this S is the only ideal of S. So let's take any ideal. Let I be an ideal of S. Then for any A in I, we have this S S it's equal to the J class of A, because the J class of A, it's a J class, those elements which are J related to its S, because S is the only J class. But at the same time, this one, it's actually subset of S1A, S1. You can see it's very simple. If you choose any element B here, you can easily verify that B is actually in S1A, S1. That's very simple. Now look at this. It's the two-sided ideal containing J. It's actually the smallest ideal, smallest two-sided ideal containing A. But I is an ideal. It means that I is two-sided ideal actually containing A. But this one is the smallest one. Therefore, this must be subset of I. As you can see, as S1A, S1 is the smallest ideal, is the smallest with respect to the inclusion relation, okay? Is the smallest ideal containing A, okay? And I is an ideal, it also contains A, so that means S1A, S1 is actually subset of I, which implies S is subset of I, but I is also always subset of S, so this gives that ideal I is equal to S. And hence S is simple. S is simple. S is simple. Okay. Now we have simple result for zero simple semigroups. So that I will leave as an exercise for you, which is the following. S is zero simple semigroup. Show that. So in that case, S is zero simple if and only if S is the only J class. Now here, look at this. For zero simple, S is zero simple semigroup. S is zero simple semigroup. S is zero simple semigroup. If and only if and S is zero simple semigroup if and only if S square not equal to 0, S square not equal to 0, that's the first condition, and 0 comma S and 0 comma S minus 0, sorry, 0 and 0 and S minus 0 or the only J classes of S, or the only J classes of S, or the only J classes. S is zero simple if and only if S cannot equal to 0 and S minus 0 and 0 and this 0 and S minus 0 are the only J classes of S. So that's an exercise for you. Okay, let's so one more exercise for you. It's again a simple, that S be a simple semigroup, then show that S adjoining 0 is a zero simple semigroup. Zero simple but converse is not true. But if S is a zero simple semigroup, then S minus 0 need not be simple, because by removal of 0, say s minus 0, it may not remain semigroup in general. So we can remove 0 only if we can remove 0. We can remove 0 only if 0 is prime. 0 is prime. That is if the product is equal to 0, this should imply A equal to 0 or B equal to 0. Then in that case, S minus 0 is a semigroup, and if S is 0 simple, then S minus 0 is simple. In that case, S minus 0 is a semigroup. Is a semigroup if S is a semigroup. If S is a semigroup. Because if you choose any two elements in S minus 0, say A is in S minus 0, B is A is not equal to 0, B is not equal to 0, then their product cannot be equal to 0, because for a product is equal to 0, one of them must be equal to 0, which is not the case, because A is not equal to 0, B is not equal to 0. So in that case, it's a semigroup wherever S is a semigroup. And you can easily verify that if S is a 0 simple semigroup, then S minus 0 is simple, and hence can say, S minus 0 is simple, and hence S minus 0 is simple, and hence S minus 0 is simple if S is 0 simple. If S is 0 simple. Okay. Now we have following important proposition which gives the criteria for a semigroup to be simple. Okay, to be 0 simple actually. And we have also same result for simple semigroup. Let's do that theorem first. So the statement is a semigroup S is 0 simple. A semigroup S is 0 simple. A semigroup S is 0 simple if and only if S is equal to S for all A not equal to 0 in S. That's for all A comma B belongs to S minus 0, both are not equal to 0, then there should exist, so B is in S and S is equal to SAS, so that B should be of the form of should be in this set SAS, that means it's of the form of X, A, Y, where X is in S, Y is in S. If and only therefore for all A be in S minus 0, then there should exist X comma Y in S such that B is equal to XAY. XAY. Okay. So let's prove this theorem first. Then we have an analog of this theorem for simple semigroups that you can do yourself. That's not a big deal. Okay, let's assume that our semigroup S is 0 simple. So suppose S is 0 simple. And we need to show that for every A not equal to 0 in S, SS is equal to S. So let's choose any element, let A not equal to 0 in S. We show that SAS is equal to S. SAS is equal to S. So how do we proceed? Since our S is 0 simple, this is given, S is a 0 simple semigroup. So then SAS is an ideal. In fact, S square is an ideal. In fact, S square is an ideal. You can easily verify that since S square is an ideal of S, it's very simple to verify. You can verify it yourself as an ideal of S. Therefore, S square is equal to S, as S is simple. It has no proper ideals, which implies S cube is equal to S also. Because S cube is equal to S into S square, that's equal to S square, which is equal to S. S cube is equal to S, and so on and so forth. Now this A is a non-zero element, so SAS, since again this SAS is an ideal of SA, and that S square is also not equal to 0, because by definition of 0 is simple. So S square is an ideal and it's not equal to 0, therefore S square must be equal to S only, because it is only two ideals, one is the 0 and second is the S, and this S square is not equal to 0 by definition of 0 simple semigroup. So it means that S square is equal to S, and then now we can see this S cube is equal to S. Again, SAS is an ideal of S, is an ideal of S. So therefore SAS is equal to 0, because it has only two ideals, and SAS is equal to S. We need to show that this one SAS is equal to S. So that means we have to negate this case. So for if possible SAS is equal to, for if SAS is equal to S, let's see what happens. It's equal to 0, sorry. It's equal to 0. It's equal to 0. Then we see this we construct an ideal which contains A. Let's see that ideal. Let's take this set. Let I is equal to those elements of S such that SXS is equal to 0. Look at this set. It contains A, then A belongs to I. And A is not equal to 0, so which implies I is not equal to 0.